In our last session, the name of the game was minimizing the RSS as a function of beta naught and beta 1. So what's going on here? Two parameters. This is a simple linear regression application where once you determine these two parameters, or at least you estimate them, what's the difference between determining them and estimating them? Even if the relationship between your variables, your predictor variables, the input variables, and your output variable is indeed perfectly linear, the data available usually isn't entirely comprehensive or entirely factual. There may just be errors, misreporting. Not to mention that the model itself isn't necessarily doing us any favors assuming linearity, and we remind ourselves of this limitation by using beta naught hat and beta 1 hat. And those would be think of it as the horizontal coordinate. Well, horizontal isn't really going to help over here. Let's call it the beta naught coordinate and the beta 1 coordinate. So that point that minimizes the surface. And what is this surface? Well, for every choice of beta naught and beta 1, and what are these? These are parameters. They are and let's highlight them, the intercept parameter and the slope parameter. And what do we mean by slope? Well, if it's a positive beta 1, that means increasing the input variable will result in an increase in the output variable. And for every possible beta naught value and beta 1 value, we have a point on this surface. We assume that there is a minimum, and that minimum is at the point beta naught, comma, or it's attained at beta naught, comma, beta 1. This is simple linear regression. We are trying to minimize the residual sum of squares made up of these n terms, where each ei is the difference between the actual and the expected. The actual is any of these red points. That's your actual raw data. If this is the training, data, the blue is your expected. You're fitting a linear relationship. So for every point, each of these vertical lines measures the distance, but this is a generalized distance. It's not necessarily non-negative. Any point below the line, we attribute a negative, we assign a negative distance to that observation, which is why we square. Now, writing each error term, we should not say error term, right? Error term is the epsilon that we've discussed in previous meetings. Each residual, E1, E2 until En, depending on how many observations one is using in their training data set, may be written as a function of the actual y and the actual x. We apply derivatives, specifically something that's known as partial derivatives, typically done at university level, which help us find the point, and we shall refer to it as beta naught and beta 1. It's going to be at around 7 and 0.047. That minimizes, that gives you the least residual sum of squares. Now we're going to assess the accuracy of these parameters. You may also use the word coefficient. Recall from chapter 2 that we assume that the true relationship, so without a hat, between x and y takes the form y is equal to f of x plus epsilon, that's the error term, for some unknown function f, where epsilon is a zero mean random error term. If f is to be approximated by a linear function, then we can write this relationship as y is equal to beta naught plus beta 1 x plus epsilon. Here, beta naught is the intercept term, that is the expected value of y when x is 0. Notice we're speaking about expectation. So think of rolling a dice with 6 sides numbered from 1 to 6. What is the expectation? What is your expected result? Well, this is something where you simply say a result of 1 has a 1/6 probability, a result of 2 has a 1/6 probability as well. And if you multiply your probability and your outcome value, you will get the expectation. Let's see if we can, let's see if perhaps we can do it in R. How would you simulate a dice or a game of dice? There's something called sample. I think we need to say, for example, 10,000 rolls of the dice. So what does size mean? This is just x is the from which to choose. So we'll say from 1 to 6. Let's do it 10,000 times. Replacement is true. We are allowed, you know, to roll a 6 more than once in these 10,000 trials, obviously. And probability, can I leave probability out? Would that just assume a uniform probability? Let's have a look. Let's say outcomes, dice outcomes, and we'll do a histogram of the dice outcomes. And what was it last time where we were using buckets? Let me just go in the book for a second. How can I reduce the number of buckets? It wasn't break, it was, yep, bricks. Bricks is equal to 6. And now this is really interesting, isn't it? Y is 1. So there might, this doesn't give the impression that it's a fair dice. Let's see if there's a binomial. Can you do a discrete? But that's not, that wouldn't work, right? Maybe do it in Excel, perhaps. Maybe do it maybe do it in Excel. Never mind. The idea is very simple. What do we mean by expectation? Expectation is another word for mean in statistics. So you have your, if it's a dice, 1, 2, 3, 4, 5, 6, each of them with a 1/6 probability. So I can take that 1/6 out as a common factor, and that's 3.5. This is what we mean by expectation. You're not necessarily going to get 3.5, and in the case of a dice, you will never get 3.5. But if you had to roll the dice a sufficient number of times, you would expect a mean score of 3.5. This is what we mean by expectation. The expectation of the error term is 0. It's a mean 0 random error term. And beta naught, as a result, is what you would expect for y when x is an input of 0, right? So here, beta naught is the intercept term. That is the expected value of y when x is 0. Just to emphasize this, if we go back to the sales data in chapter 2, over here, what we mean by expectation is, let's say x is 30. Let's say x is 30. Well, when x is 30, you do not have just a single observation. You have roughly these. So if you want the expected sales, you would need to average this value, these two values, etc., etc. Hopefully we get the picture. Remember, it's this error term means that you would usually not expect all the data to line up perfectly on the line. When x is 0, I mean, in this case, we have no data for obvious reasons. If the sales budget is 0, or no, actually, we do have. So we actually have a couple of observations where, and each data subject was a market. So think of each red point as representing the data for maybe different geographical regions. So for example, in the US, we have maybe the 100 largest cities where we are advertising. At zero, we get this beta naught value. This would be beta naught, would be over here, just under 10. And that's telling you we would expect if the blue fitted model is giving us any indication of the underlying reality, we would expect that when our sales budget is 0, that we would have beta naught units of sales using this specific marketing example. Let's go back to chapter 3. I'll read it one last time. Here, beta naught is the intercept term. That is the expected value of y when x is 0. And beta 1 is the slope. Again, the average increase. So mean, expected, and average, very often they are used interchangeably. The average increase in y associated with a 1 unit increase in x. The error term is a catch-all for what we miss with this simple model. Now, every model is a simplification of reality, which is why even in the true relationship, even in the true form, you need an error term. You need an error term. Why do we say that a model simplifies reality? Because it's only taking, and remember, this is usually a vector, not in simple linear regression. So although we're using the same notation, we should perhaps use different colors over here. The pink is quite different to the orange. In the orange, we're allowing x. We usually enumerate them from 1 to p. The orange is allowing p variables for each observation: age, sex, political affiliation, left-handed, right-handed. You could have so many different variables. In simple linear regression, again, although we're using the same notation, that there's nothing that distinguishes this x from this x. In the pink, that is a specific value. That is a real number. One variable, only one variable, only one variable. The error term is a catch-all for what we miss with this simple model. The true relationship is probably not linear. There may be other variables that cause variation in y, and there may be, I was thinking of this earlier, there may even just be measurement error. So you know, just the data itself isn't perfect. We typically assume that the error term is independent of x. It's not always the case. The model given in 3.5 defines the population regression line, which is the best linear approximation. Now, what do we mean by best? To the true relationship between x and y. And we have a footnote. The assumption of linearity is often a useful working model. However, despite what many textbooks might tell us, we seldom believe that the true relationship is linear. The least squares regression coefficient estimates, 3.4, these two, this is how we are, this is what we mean by the best fit, the best linear fit, the best linear approximation. With respect to what? With respect to reducing the RSS. Reading on, the least squares regression coefficient estimates 3.4. Oh, actually what they're saying is the least squares regression coefficient estimates, not a verb, characterize the least squares line, 3.2, the least squares line, this, the left-hand panel of figure 3.3, which is next page, displays these two lines in a simple simulated example, which is very similar to what we did in our previous session using Excel. We created, I think we had only created around, it was less than 20. The authors are taking 200 random X's and generated 100 corresponding Y's. And they've actually told us what they've done this time. They've been a bit more specific than in previous charts. They're telling us the true relationship, remember, you're playing God, you're omnipotent, is f of x is 2 plus 3x. We're approximating it using the, is it the blue? I think it's the blue, yes, exactly. Right, so the authors took a red line, they took an error term, they created the 100 data points using the method of least squares, which reduces the residual sum of squares, we obtain, all you need is two parameters, beta naught and beta 1. Those two parameters give you the blue line. How did they generate these black data points? From the model, y equals, notice no hats, we're omnipotent, 2 plus 3x plus epsilon. And you will notice your, do take care. This is not the vertical axis. The vertical axis is over here, okay? It would be right in the middle. And that would intersect the red line at 2, because they're taking an intercept term of 2, where epsilon was generated from a normal distribution with mean 0. They don't reveal the standard deviation, but they do specify that the mean, remember, every random variable has one or more parameters. A normal distribution, and we don't mean normal in just the day-to-day usage of normal. We don't mean, what example could we take? A normal chair withstands 150 kilograms of mass. It's just maybe a slightly misleading term. I think it comes from something to do with 90 degrees and cosmological observations. You're measuring stars. Maybe you have two telescopes at 90 degrees to each other. It has nothing to do with normal, as in we would say, you know, a normal human being, whatever we would mean by a normal human being in any case. The red line in the left-hand panel is the true relationship. The blue is the fitted relationship. The true relationship is generally not known. That's the whole point of modeling in the first place for real data. If you knew it, then there's no statistical learning to apply. You know everything once you know the true relationship. But the least squares line can always be computed using the coefficient estimates given in 3.4. We have these two formulae which are solving a pair of simultaneous equations where you're equating the gradient to 0. In other words, in real applications, we have access to a set of observations from which we can compute the least squares line. However, the population regression line is unobserved. In reality, you will only have the blue line. You cannot simply say, oh, does my blue line look, whatever we mean by look, does my blue line look like it's close to the red line? The red line is not available. That's the point of creating a model, of applying these statistical learning techniques. You will only have the black data. Least squares regression, minimizing the RSS, creates the blue line. And if this is sounding repetitive, it is repetitive. I may even be repeating more than the book over here, which it's saying something, isn't it? However, the population line is observed in the right-hand panel of figure 3.3. We have generated 10 different data sets from the model given by 3.6. So, okay, what's going on over here? What's going on? Didn't we have 100 data points over here and we fitted the dark blue line? They've done it 10 times. Each of these 10 times, they've generated 100 random variables, beg your pardon, 100 random observations based on the red line, and then they fit a linear model to that data. So just like we created the blue line, the dark blue line, based on this collection of black observations, we do it 10 times. So imagine I had to go out and collect data, but you do the same thing and you collect your own data. We're all going to have a slightly different model, assuming, as you would imagine is the case, assuming that the data that I collect isn't perfectly aligned with your data. There might be biases. The data we may be measuring differently, etc., etc. At first glance, the difference between the population regression line and the least square line may seem subtle and confusing. We only have one data set, and so what does it mean that two different lines describe the relationship between the predictor and the response? Fundamentally, the concept of these two lines is a natural extension of the standard statistical approach of using information from a sample to estimate characteristics of a large population. Let's take it closer to home. Probably the example that most of us are familiar with is election polling. And there's quite an important election tomorrow, right? There's the midterms in the US where I guess Senate might be up for grabs, possibly even Congress. And these are examples with real life implications to millions of people where it might make a difference to laws that are passed, to the effectiveness of government, to which wars are going to be waged within the next 2 years. You never know the full picture. You cannot, if it's a country like the US, we're speaking of hundreds of millions of voters. Granted, most of them don't actually turn up on election day, but they have the right to vote. It is nearly humanly impossible to know the voting intentions on a specific day of the entire observation, of the entire electorate, is what I should have said. That's made up of data subjects. So you will only have a sample. Now, you would want your sample to be representative, so you're hardly going to only ask people from a very specific city, but because there are biases over there. So it needs to be comprehensive. It needs to involve enough people that you get a bit of statistical credibility. It needs to be trustworthy. There's a phenomenon known as the shy Tory. Tory, it's the Conservatives, right, in the UK. And the shy Tory phenomenon, you've probably heard of it, is that polls consistently, and there's a similar effect in the US as well, polls consistently diminish they underestimate of the conservative vote, the percentage of the population that's going to vote for Conservative Party. Going back to the book, for example, suppose that we are interested in knowing the population mean. Mean means just average, and this is standard notation, mu, just letter M, right, for mean, Greek alphabet, of some random variable y. Unfortunately, mu is unknown, but we do have access to n observations from y, which we can write as y1 until yn. Notice we're not mentioning x's. We're not talking about a relationship over here. Here, this is like O-level data handling, where I simply tell you, I have a warehouse with 1,000 computers, and I give you the data, the manufacturing year of each item. And then you can perform summary statistics. Minimum, maximum, first quartile, third quartile, the median, mode, mean. We've been discussing standard deviation. That's not at secondary school, although you do try capturing it very simplistically with the concept of range, not range of a function, range of a data set, just the max minus the min. So if you have access to n observations, you can estimate mu. A reasonable estimate, you could just say, okay, well, I think that the population mean is equal to the sample mean. Population mean, the true population mean is mu. I can estimate it. So since we're speaking of an estimate, mu hat, I can say that an estimate, let's emphasize these things. I could say that I can estimate the population mean, that's pink. I can estimate it using y bar. What is y bar? Y bar is just it's just how you calculate mean, right? By the way, you're assuming that all observations are, you're weighting them all equally. You're just saying one observation was as equally likely as the other observation. You're just adding all of them and dividing by the number of observations. The sample mean and the population mean are different, right? In all likelihood, they're not going to coincide perfectly unless we're really lucky. And even if you get really lucky, do you know that you got really lucky? There's always that uncertainty in these estimates. So the sample mean and the population mean are different, but in general, the sample mean will provide a good estimate, whatever we mean by that. Notice sometimes you cannot be precise. We will, at least at these early stages, there are still things that aren't necessarily, defined mathematically. We're just going like kind of by intuition, by gut feeling. We're just saying a good estimate. Okay, what does that even mean? Within 1%, within 10% of the population mean. In the same way, okay, now going back to linear regression, going back to these betas that we need to estimate. In the same way, the unknown coefficients beta naught and beta 1 in linear regression define the population regression line. So wait. What's going on over here? What's going on? You have your actual, which the book is going to refer to as your population. I'm more familiar speaking at work in terms of actual versus expected, but you have your actual regression line, the true relationship, right? The true relationship. Your actual regression, you will estimate it using these betas. These coefficient estimates, now from where are they derived? They're defined by least squares. Okay, where's my cursor? The analogy between linear regression, which is what this whole chapter is about, and estimation of the mean of a random variable, which is basically what O-level, secondary school is about, is an apt one based on the concept of bias. If we use the sample mean mu naught hat to estimate mu, this estimate is unbiased in the sense that on average, So if you pick an average data set, just a typical data set, and you do it 100 times, and you estimate, each data set gives you a different estimate of mu hat. Now, if you average all those estimates, you would expect that mu hat is, roughly equal to mu. Let's see. And in fact, I'm sure the book is going to do a better job. Let's read it. What exactly does this mean? It means that on the basis of one particular set of observations, one particular set of observations from y1 to yn, mu hat might overestimate mu, and on the basis of another set of observations, mu hat might underestimate mu. But if we could average a huge number of estimates of mu obtained from a huge number of sets of observations, then this average would exactly equal mu. This is the concept of an unbiased estimator. It's actually a recurring idea in statistics. So just to make this entirely clear, if each one of us in this meeting, we say we would like to estimate the mean, think of it as the average, the mean height of 15-year-old boys living in country XYZ. I collect a set of data, a particular set of observations. Each one of you collects your own data set. We haven't interviewed everyone, right? And even so, there are still errors. There are still errors in the way we measure, in what do we even mean by someone who's 15? Do we mean someone who turned 15 today? Each one of us calculates their mu hat. Then we bring all the mu hats together and take the average of that mu hat, of those mu hats. Well, the way this is set up, you can mathematically prove that if we're calculating our mu hats using the mean, not the median, not the mode, not the geometric mean, there are many ways of averaging. If you use mean, that creates what we're going to refer to as a unbiased estimator. That the average of the means would exactly equal the true population mean. It's quite a lot to get your heads around, but just the idea, think of many people going out and collecting their own data set. The average of the means of all those data sets should exactly equal the true population mean. These overestimating and underestimating, they kind of zeroize each other out. Hence, an unbiased estimator does not systematically over or underestimate the true parameter. The property of unbiasedness, okay, something that's not biased, the property of unbiasedness holds for the least squares coefficient estimates, given by 3.4 as well. If we estimate B naught, beta naught, and beta 1 on the basis of a particular data set, then our estimates won't be exactly equal to beta naught and beta 1, right? So if you're doing this on one specific data set, which is what's going on in the first diagram, on one particular data set, you're not expecting your beta naught and your beta 1 to coincide perfectly with the 2 and the 3, because there is an element of bias in the data. You only have 100 observations. Let's look. So if we estimate beta naught and beta 1 on the basis of a particular data set, then our estimates won't be exactly equal to beta naught and beta 1. But if we could average the estimates obtained over a huge number of data sets, then the average of these estimates would be spot on. In fact, we can see from the right-hand panel of figure 3.3, that look, some of the blue are above the red over here, some of them are below. And if you average all these blue lines out, now these are only 10 of them, but if you average all these blue lines out, you would get closer to the red line. The red line is the true relationship, the population regression. In fact, we can see from the right-hand panel of figure 3.3 that the average of many least squares lines, each estimated from a separate data set, is pretty close to the true population regression line. We continue the analogy with the estimation of the population mean, mu, of a random variable y. A natural question is as follows. How accurate is the sample mean mu naught as an estimate of mu? Earlier I said they must have used the word like good. Yeah, good estimate, which mathematically, scientifically means next to nothing. It's undefined. You haven't said anything over there. Now we're going to measure that goodness. The natural question is as follows. How accurate is the sample mean mu hat as an estimate of mu? We have established that the average of the mu hats over many data sets will be very close to mu, but that a single estimate mu hat may be a substantial underestimate or overestimate of mu. Now, this is the question, right? How far off will that single estimate of mu hat be? In general, we answer this question by computing. This is an extremely important measurement. The standard error of mu hat, written as standard error, or SE, of mu hat. We have the well-known formula. Not to worry, if you asked me to quote this, I would have had great difficulty recalling it. So standard error of mu hat is the square root. So if you square it, we define it as sigma. Now, what on earth is sigma? All over n. We know what n is. N is the number of observations. And does it make sense to you? The larger the n, the more data points you're including in the calculation of the sample mean, then you would expect it to be inversely proportional to the standard error. The lower, actually, let's talk about the higher. The higher the n, the lower the standard error, right? You have more data, the larger. The way we're defining standard error, it is inversely proportional to the number of observations. It's directly proportional to what? To this sigma squared. Now, what on earth is sigma squared? Well, we'll let the book explain it in a more rigorous way. What I will just say is the variability within your data. So if we're looking at 15-year-old boys in country XYZ, and they are all the same height, that's zero variability. That's zero variability. There is no, the data is perfectly homogeneous. What you will usually have is the opposite. You will have heterogeneity, and sigma is one way of measuring. You can think at looking at the stock market. If you're looking at the one day movement, so of the past year, you have 365 percentage movements, and you could look at the variability within that data set. Just to take a simple example. Now, where sigma, and don't let these formulae put you off, where sigma is the standard deviation of each of the realizations yi of y, and that's a footnote. But just before we actually look at this footnote, let's create some data, and let's say, for instance, shall we take binomial? Shall we take uniform? Why don't we take uniform? So R uniform. Does tab not work? We'll say, let's generate 1,000 data points from whatever, right? From 8 to 10. You're going to see very soon what these 8 and 10 are. Okay, that's them. Histogram. Let's call this my data. My data. As you can see, it, uniform, right? Practically self-explanatory. In each bucket, so there's the bucket from, let's say we took eight buckets, although R doesn't always give exactly 8. And in fact, yeah, it hasn't changed it. What if we take 10 buckets? What if we take 2 buckets? Okay, so you can see why we're calling this uniform. There is roughly no difference. Statistically, it would be, what's the word? Statistically insignificant between the values, between the number of values between 8 and 9, and the number of values between 9 and 10. Now, why are we doing any of this? Let's go back over here. First of all, you can calculate the mean. You'd expect the mean to be around 9, right? Mean of my data, and it's, yeah, to 2dp, it's 9, right? 9.00. And now we can also calculate the standard deviation. This is just to get an idea of the variability. Remember, I could create another 1,000 randomly generated. I use the normal distribution, and what I say is, this is a bit cheeky, but there's probably an easier way of doing it. But I could say the mean is this, and the standard deviation is 0. So what does this do? These are all 8, each data value. Let's call this my normal data. My normal data. Well, that's going to be, that's going to have the same mean, right? Mean my, so look, same mean, both of them. Now, of course, there's a major difference. The difference is, going beyond the mean, the variability. So at secondary school, we would have said that this data has a range of 0. take your minimum, you take your maximum. They're both the same number because all values are the same, and that range is 0. Now, whereas over here, this range isn't going to be 0. It's probably going to be around 2, right? Roughly 10 minus 8. So to capture that variability, there's something called the standard deviation. And I'm not sure how to do it in R. I think you need to calculate the variance first. So the variance of my data. And then you square root everything. There's probably a single command, but the definition of standard deviation is just the square root of the variance. So look at the difference. Look at the difference. So we have 0 standard deviation, which basically means it's not a random variable. If it's 0, there is no randomness, so to speak. Whereas the my data, there is variance, there is standard deviation, there is variability. Just intuitively, certain words, maybe we're repeating them a bit too often, but variability is really the underlying concept of all statistics, right? I just said if it was 0, then it wouldn't be a random variable in the first place. It would be it wouldn't be stochastic is the word, a stochastic process, a random process. Random, you may know the probability distribution, and you would hope to know the probability distribution, but it's still random. Think of a coin toss. You know the distribution, it's heads, tails, 50-50, but it's a stochastic. It is random. The opposite of stochastic is deterministic. It's predetermined. You know what's going to happen. It's deterministic. And this is all we mean. You calculate you measure the standard error of your estimate of mu hat. So this is the estimate of the population mean. Using this formula, you square root the standard deviation squared all over n. This formula rewards you. When I say rewards you, you want your standard error to be as low as possible. It rewards you for taking the larger your data set is, so you get a larger reward depending on how large your data set is. It penalizes you, and in fact, that penalization is squared based on the standard error. This is something you usually cannot control. You cannot control that. Standard error is, I mean, if it's, I'll go back to the height of people, you can't control the standard deviation. You can't control the variability within if you're trying to model height, you can't control that. But what you can do is the higher the standard deviation is, you can counteract it by taking a larger and larger data set. Okay, so again, you can't really control sigma. Sigma is just a naturally occurring feature of the data that you're trying to model. That's squared, so you have no control on the numerator. It just depends on the work that you're performing. So for example, take insurance. What do we want? What do insurance companies want? They want the lowest possible volatility, variability within the business that they sell. So for example, non-life insurance, also known as property and casualty. So think of your motor insurance, your cyber risk, your professional indemnity, the one that accountants take out, the one that actuaries take, the one that doctors take. Sometimes that is, depending on the jurisdiction, that could be compulsory. So usually the biggest danger to non-life books of business is catastrophes, natural catastrophes. So going back to 1992, Hurricane Andrew, the damages were unprecedented. Obviously, you need to see how much of the damages were actually insured by your insurance companies. So very often these major catastrophes in the less developed part of the world, the damages are in billions, but for numerous reasons, sometimes even along religious lines, where you're kind of trying to defy your creator or the gods. Insurance is frowned upon or not easily available. The impact to insurers is actually minimum. But Hurricane Andrew, going back to, was like 92, 93, that was the first time. That well, definitely wasn't the first time. That's a gross exaggeration. But it's where actuaries, you started seeing the shift from the more traditional career paths, which for an actuary is always life and pensions, to non-life. So there was this transition. It's known as non-life in continental Europe. It's known as general insurance in the UK, and it's known as property and casualty in the US. Those are the three regions I'm most familiar with. So you cannot control sigma. I mean, if you're an insurance company, you can, I guess you can say, if you think that, I don't know, insuring doctors in a specific region opens you up, exposes you to a large sigma, you may, not necessarily, but you may have the option just not to write that business. You say, hey, I'm not going to offer professional indemnity to doctors. And I say that because sometimes insurance companies are compelled to offer certain types of insurance. So, for example, I think in France, there is the terrorism insurance. For example, if you're writing, and do not quote me on this, it's just from what I know by osmosis, but if you're writing motor business, you cannot, for example, say, yeah, I'll insure your car, but if the damages occur in a terrorist attack, oh, by the way, what do we mean by a terrorist attack? Usually this would be, it has to fit certain criteria. You may even take an insurance company to court. It might be that an insurance company is saying, this was not a terrorist attack, so I don't need to pay you. And then you take them to court, and sometimes it comes down to just a court decision. What do we mean by terrorism? Although very often these are, and you know, we experienced this recently with the pandemic. If the WHO was so reluctant to officially label it as a pandemic, among a variety of reasons, you know, not trying to create a panic, waiting for more data, seeing how the thing evolves. One of them is, as soon as you've called it a pandemic, that's when many exclusion clauses react. It's not the word react. In Maltese, you'd say "jiskatta." So anyway, they activate, right? They activate, and all of a sudden, the insurance companies are off the line if they have certain exclusions which can be enforced, just in a court of law. So you have no control. You have no control on your sigma if you're looking at, I want to look at this specific variable. You can't control that sigma, but you can counteract it by taking larger and larger observations. Okay, and we have a footnote. Let's see. This formula holds provided that the n observations are uncorrelated. I see. Okay, so you would use this formula if the observations are uncorrelated. But in this context, if we're looking at one variable, going to be entirely honest, I'm not 100% sure what they're getting at when they say we'll have to look into it. Moving on, roughly speaking, the standard error tells us the average amount that this estimate mu hat differs from the actual value of mu. So what we're looking at is the standard error is saying, take an average mu hat, take your population mu hat. Now remember, you don't know the population mu, but what you could do is once you calculate the standard error, you could say, okay, I know my standard error. I've calculated my mu hat, so the true population is between mu hat plus the standard error and mu hat minus the standard error. You would say that you would conclude, and there are measures of credibility, which we'll probably get into at some point. For example, you would say, I'm 95% certain that the true population mean, that the actual, oh, look, they're using actual now, that the actual mu is within a specific interval. How is that interval created? We are modeling real numbers. So you'll take your real line, you have your mu hat, this is your mu hat, you calculate your standard error based on the formula that we saw on the previous page, and you'll say standard error to the left, same thing. Let's place it on the right, and you will say my true population mean is within this interval. Of course, you want to minimize the width of that interval. The narrower it is, well, the more certainty you have in future predictions. And that is there's this dance between sigma and the number of observations. Again, it's worth rereading. Roughly speaking, standard error tells us the average amount that this estimate mu hat differs from the actual value of mu. Equation 3.7, so that's what we saw earlier, sigma squared division by n, also tells us how this deviation shrinks with n. The more observations we have, the smaller the standard error of mu hat. Okay, now, that's kind of like O-level statistics. Granted, we don't discuss that formula at O-level. But now we're going to go to the next step, and we're going to look at the error within our beta naught hat. If there's a hat, there's always an error, and beta 1 hat. In a similar vein, we can wonder how close beta naught hat, and beta 1 hat are to the true values, beta naught and beta 1. To compute the standard errors associated with beta naught hat and beta 1 hat, we use the following formulas. And this is really interesting. It's the first time that we're discussing that we're using the error term within our formulae. Where we see sigma squared, and notice the parallels between the previous formula. Sigma squared is always in the numerator, directly proportional, the standard error, and sigma hat is the variance of the error term. So the larger the error term, and what does the error term do to your data? The error term just means that the larger the error term is, that doesn't make sense, right? The larger the variance of the error term, the larger these pink arrows will be. These pink arrows over here, the larger these pink arrows. And that will just be a natural feature of your data. You can't change that. You can't change that. You can't. Okay, I mean, one thing you could do is you could maybe, instead of saying the heights of 15-year-olds in a specific country, maybe you could separate the data and say these 15-year-olds that had this diet, these 15-year-olds that had that suffered a certain illness, and you partition the data. Yes, there's more homogeneity, but what happened? Did we notice what happened over there? You have a lower n now. If you have your data set, if you have 1,000 data points, and you're partitioning, it is true that for every partition, you are likely to reduce the variability, the sigma. What's happened though is you've also reduced your n. So the effect could be quite minimal. For these formulas to be strictly valid, we need to assume that the errors, EI, where were we? I'd appreciate when it's close to 10, if one of you could just send a message in the chat. Close to 11, right? Yeah, I think we're long past 10. For these formulae to be strictly valid, we need to assume that the errors epsilon I for each observation are uncorrelated. This is clearly not true in figure 3.1. Do you know what they're saying over here? This is a point where we don't really need to. I think there's a word called heteroscedasticity. Are you noticing that as we move, as the input gets larger, the pink arrows seem to get longer compared to these green arrows over here, right? So strictly speaking, let's see how the book worded it. Next page, right? The error of each observation, epsilon I. Don't muddle it up with EI. EI was just when we're doing linear regression. E is the residual. E is your actual minus your predicted or your expected. These are the error. These are the EIs. The epsilon, not E. The epsilon I. Notice in the formula that the standard error of the slope, right? Beta hat 1 is the slope of the line that you're fitting, is smaller when the xi are more spread out, right? Look, the larger the difference, the greater the difference, between each x So the input variable from the mean of x, the larger this difference, the larger the denominator, so the smaller the standard error. Intuitively, we have more leverage to estimate a slope when this is the case. What does that mean? What does that mean, more leverage? It's one thing if you only have points here and you're trying to fit a line. The further spaced out the points are horizontally. This reminds me of when I was when we used to have physics, when we used to have lab reports, they used to tell us like take your data as far out as possible and then try joining a line. The book is referring to it as more leverage. We also see that the standard error of beta naught would be the same as the standard error of mu hat. Oh, right, look, see? Sigma squared all over n. It's like the previous formula. Sigma squared all over n. But there's an additional term. Would be the same if x bar were 0. Ah, x bar were 0. Huh. I'm not following. If x bar was 0, this wouldn't become 0, though, would it? I don't think so, right? In which case, beta hat naught would be equal to y bar. Not entirely following. We also see that oh, right, because this x bar would be 0 as well. Yes. Okay, I didn't pay attention to the numerator. If this were 0, if x bar were 0, if the mean is 0 of the x data values, this numerator is 0, 0 squared. 0 divided by anything, as long as you're not dividing by 0, is 0, and you're back to, you just have sigma squared over n. This estimate is known as the residual standard error and is given by the formula RSS, which is the residual square sums. These take the difference between the actual and the predicted, square it, and add over all the observations. So if you do the RSS divided by n minus 2 square root, you get the residual standard error. And what is this the same as? This estimate. Which estimate? For beta naught. Strictly speaking, when sigma squared is estimated from the data, we should write standard error hat. Standard error. So they're saying you really, what you need is a hat over here as well. Why? Well, because usually you won't know sigma either. This would actually be an estimate. That would be an estimate. But for simplicity of notation, we will drop this extra hat. Now, this is what I was getting at earlier. Standard errors can be used to compute confidence intervals. A 95% confidence interval is defined as a range of values such that with 95% probability, I wish they wouldn't use range. We should say interval. Range already means a number of things to us. We have at secondary school, range means the max data value minus the min data value. Pure mathematics, although quite an abstract concept, right? There's the range of a function, so the set of all outputs of that function. So if it's f of x is equal to x squared, you can never get a negative output if you're working with real numbers, of course. If every input is a real number and you square it, you can never get a negative. So the range of f of x is equal to x squared is the set of real numbers greater than or equal to 0. I'll try saying interval. It is the actual terminology, in fact, confidence intervals. The interval will contain the true unknown value of the parameter. This is what we said earlier. The interval is defined in terms of lower and upper limits computed from the sample data. This is when I drew those orange arrows and I drew an interval. For linear regression, the 95% confidence interval for beta 1 approximately takes the form. Okay, so what's happening? You have your data, you fit a blue line, you fit the blue line by calculating beta 1 hat and beta naught hat. Now you want to know what is the true beta 1, what is the true slope? The true slope is found by doing this over here. Take your beta 1 hat and to the left and to the right, plus or minus 2 times standard error of beta 1 hat. So you've calculated your standard error of beta 1 hat, square root it, just get rid of this square, multiply it by 2, and that's given you the confidence interval. That is, there's approximately a 95% chance that the interval, this over here, are we familiar with this notation? This is square bracket notation. This is just representing an interval. It just means from this number to this number, okay? They've taken the plus or minus, gone to the left, gone to the right, will contain the true value of beta 1. Now, approximately for several reasons. Yes, so for example, if you're asking where did the 2 come from, that comes from a specific probability distribution. Equation 3.10 relies on the assumption that the errors are Gaussian. Gaussian means just normal distribution. Also, the factor of 2 in front of the standard error of beta 1 hat term will vary slightly depending on the number of observations n in the linear regression. And this is interesting. To be precise, rather than the number 2, 3.10 should contain the 97.5% quantile of a t distribution with n-2 degrees of freedom. And we're going to see this in R. The important thing is that you're just being exposed to these ideas. Similarly, a confidence interval for beta naught approximately takes the form this over here. With these two pieces of information, you now know, remember, you never know the red line. The red line is the true relationship, but you now can estimate, okay, the red line should be somewhere within, I guess what you get is, you get some kind of like rectangle like this. And you'll say, okay, roughly the red line should be somewhere in this rectangle. That's the idea. Can even see it in Desmos at a later stage. In the case of the advertising data, the 95% confidence interval for B naught is from 6.13 to 7.935. And the 95% confidence interval for B1, beta 1, is that interval. Therefore, we can conclude that in the absence of any advertising, sales will on average fall somewhere between, and this is just because it's these values are in thousands, 6,130 units and 7,940. Okay, this is what you need to go to the board with when you're presenting your results. You cannot simply tell them what was earlier beta not hat. Was 7.03. You need to give them an idea of the uncertainty. That's even in actuarial, it's called technical standards. When you're producing work that is technical in nature, what do we mean by technical? Just go with it. You need to state your assumptions, you need to list all the data used, justify the models. One of them is you need to give some kind of interval like this. It's also a way that we kind of protect ourselves, just in case someone gets into their heads that our crystal ball is infallible. Furthermore, okay, now we're going to look at the beta one. For each $1,000 increase in television advertising units, there will be, on average, 42 increase and 53 increase. Think of these as pessimistic and optimistic as well, by the way. Okay. Standard errors can be used to perform. Okay. This might be a bit tricky. Standard errors can also be used to perform hypothesis tests on the coefficients. The most common hypothesis test involves testing the null hypothesis. What do we mean by a null hypothesis? Null hypothesis is normally the conservative bet. So, for example, the null hypothesis would be there isn't a teapot. There is not a teapot orbiting the Earth. That's the null hypothesis. Then the alternative hypothesis would be there is a teapot orbiting the Earth. But you don't use them interchangeably. You'd normally say, in the apps, this is like innocent until proven guilty. The innocent is normally the null hypothesis. You assume, at least in civil and criminal courts, I think if it's a court martial, in military, do they start from the assumption that you're guilty? Possibly, or they did at one point. The null hypothesis, if maybe we're not too familiar with these ideas, think of the null hypothesis as the concept of innocent until proven guilty. So innocent is the null hypothesis. Then there's the alternative hypothesis, guilty. Now over here, what do you assume? You should never start assuming by saying there is definitely a relationship between these two variables. You cannot say, okay, this specific cryptocurrency depends on, its price depends on, or its price next week is going to depend on the share price of Twitter. Yes, maybe there might be relationships, and quite a bit of correlation. Although crypto was meant to be a hedge against inflation and other movements. So your H naught is the null hypothesis, and you start out by assuming there's no relationship, obviously. Now, the alternative hypothesis is that there is a relationship. Now, mathematically, what does this boil down to? It should be pretty obvious. There's it's a zero slope. That is no relationship. There's zero slope. changing x does not change y. Well, the alternative hypothesis, notice the A. I think the A depends on the confidence interval. No, I think it's just, okay, I'm used to H naught and H1. Oh, A for alternative, well, clearly. Since, okay, so why? That's what we said, right? If beta 1 is 0, then the model reduces to y equals beta naught plus epsilon. And notice the disappearance of x. X is not associated with y. To test the null hypothesis, we need to determine whether beta 1 hat, our estimate for beta 1, is sufficiently far from 0. So look at this, for example. Is 0 contained within, oh, sorry, over here. Is 0 contained within this interval for the slope? No. And that's a indicator that there is a relationship between the marketing budget and the units sold is sufficiently far from 0 that we can be confident that beta 1 is non-zero. Okay, now notice these are things that we should be picking up on. As soon as you see something like sufficiently far, that means nothing. I mean, it's very extremely subjective, but we're going to codify it mathematically. Let's see. Well, this of course depends on the accuracy of beta 1 hat. That is, it depends on the standard error of beta 1 hat. If standard error beta 1 hat is small, then even relatively small values of beta 1 hat may provide strong evidence that beta 1 is not 0. And hence there is a relationship. So for example, look at this. I guess our lower bound is sort of close to 0, whatever close to 0 means. But the smaller, the narrower this interval is, then the more certainty you have that 0 does not lie within this interval. How are we doing for time? Yes, okay. It probably we should conclude over here. Next session we'll start, we'll do a quick recap of this hypothesis testing. And then we'll move on to assessing the accuracy of the model. So we're actually doing very well. And a lot of these ideas, they are repeated, but we shall end it right now. Thanks, everyone.